Hi everyone, I'm back. So my name is Jean-Claude Borvel from Diana FIA, and I will be giving this e-learning session today. I see from the attendee list that there are some names that are familiar, so I assume that you are now aware of our e-learning session and the way we do this presentation. So today I will give a presentation of heat flow in prefabricated floor. I will first start with a short presentation to give you some insight about the capacity of Diana in terms of heat analysis. And then we will move to a live demo where we will go step by step through the modeling of a prefabricated floor, and then we will perform a steady state heat analysis. So having said that, let's start with our presentation. So basically, heat flow analysis is a potential flow analysis where the potential is temperature T. In Diana, you can perform two types of heat flow analysis. The steady state heat transfer analysis, where you can consider a linear solution in terms of constant conductivity, convection coefficient, or a nonlinear solution by means of temperature-dependent conductivity, convection coefficient, or radiation or cooling pipes. And the second type is a transient heat transfer. In that case, you introduce a time dependency for the boundary condition. For instance, you are talking also about capacity and duration of heat source. The general form of the heat flow equation is a diffusion equation where C is the capacity, K conductivity, and Q the rate of energy due to a source sink. For a steady state analysis, which will be our focus today, this equation can be simplified since we do not consider the time-dependent part. Typical heat flow outputs in Diana are the temperature, T, the nodal heat flow, the heat fluxes and discharge, and also maturity in terms of equivalent age or degrees of reaction. Regarding the boundary condition, you can consider three classes. The essential one, also called the Dirichlet boundary condition, where you prescribe temperature on boundary. So you assign a certain temperature TB, for instance, or a fixed temperature, 0. The natural one, also called the Neumann boundary condition. In that case, you prescribe the flux. And the last one, the mixed one, also called the Neumann-Robin, for which you need to use a boundary element. I will go a little bit in more detail through this different boundary condition because this is essential for this analysis type. So let's have a closer look to this different heat flow boundary condition and the way they are basically defined in Diana, because that's actually the interesting point. Starting with the essential one, so how can you prescribe the temperature? You have two options, whether you fixed, so you assume that the temperature is 0. In that case, you can do that using the attach fixed temperature option in Diana. And you just select the phase where you want to have, where it can be a phase, an edge, or a corner where you want to fix this temperature. And this will appear under the fixed potential. If you want to prescribe the temperature, so you mean you want to assign a certain value, then you use the attached thermal boundary condition. and you choose for the prescribed temperature in terms of boundary condition type. You define the value of this temperature, and again, you select to which part of your geometry this should be assigned. And this condition will appear under your boundary conditions as a prescribed temperature. Regarding the flux, so for the natural boundary condition, let's say, again, you can whether fix the flux or prescribe it. In the case you want to fix the flux, basically you don't need to specify any boundary condition. No boundary condition means no flux in Diana. In the other case where you want to prescribe the flux, give it a certain value, then you again use the attached thermal boundary condition, as we did for the prescribed temperature, but then you select the type thermal flux, you define the value of your flux, and then you assign the geometry part. And again, this will result in a prescribed flux condition under your boundary condition. Regarding the mixed boundary condition, you may consider three types, let's say. The convection only, which is case A, the radiation only, which is a case B, or a convection plus radiation, which is a case C. And in these three cases, you will need to make use of boundary elements, which will come on top of your structural element. Let's go through these three cases A, B, C. So in the case of convection only, what are the different steps needed? You first need to define a fixed, a prescribed temperature, an external temperature, let's say, and you do that via the attached thermal boundary condition. Here, for the type, you choose the external temperature. This is important. You specify the value of this temperature, and then you define your interface. In that case, it will be boundary interface element. So it will be flow boundary interface, actually. And you do that from the connection property assignment, but you can open directly from the attached thermal boundary condition. For these boundary elements, you need, of course, to define on which geometry component they apply. So it could be face or an edge. So the type, the element class is flow boundary. You assign an element, a material class to them, which is a heat flow material class, and for which basically you define an heat transfer coefficient. And here in the discharge type, you can choose for convection only. That's where you specify this convection type. Once you have done that, the flow boundary you have created appear under your connection box, and you can activate them by checking on these boxes. And then when you create apply, it will create a boundary interface with the name with the type flow boundary under your connection, meaning that your flow boundary elements have been created and have been activated. Basically, the same story apply when you go for radiation only, with two differences. At the level of defining the attached thermal boundary conditions, you need to specify the boundary condition type as radiative temperature. And again, you specify your value. Same story, you define your boundary interface and material associated to this boundary. But for the property, for the discharge type, then you choose radiation only. Then again, your interface are created. You activate them by checking on the box, and it will result again in a new set for your boundary interface. Finally, when you go for convection and radiation, the same story applies. You have to define two type of thermal condition. Sorry, I had to go. In which you define both thermal boundary condition, external temperature and radiative temperature condition, and for the material of your boundary elements, here for the discharge type, you can choose for convection and radiation. And again, you activate this interface when they are created, and it will result in a new boundary set. So the procedure is relatively standard. What's important is to distinguish between convection only, radiation only, and convection and radiation, and also to create this flow boundary interface for this mixed boundary condition. Having said that, we are going now to move to the live demo. I don't want to go into much detail through the theory part. I think it's better to go through the example and to see step by step how we are going to make that in practice. But first, I want to say a few words about the model of today. So the model is a prefabricated floor. You can see the cross section on this slide. It consists of three layers: a prefabricated insulation of expanded polystyrene foam. A concrete floor is casted on top of the insulation, and the top of the floor is finished with a cement sand screed. And the aim of this live demo case is to determine the heat flow through this structure for a temperature difference of 10 degrees at the outer surface, because we have 10 degrees at the bottom and 20 at the top. And because of the symmetry of the model, we will only model half of this structure. Okay, so let's move to the live demo. I apologize in advance if the reaction of my screen is a little bit slow, but I think it will be fine. So we are going to start our live demo, and as usual, we need to define a new model. So today I'm going to define it live demo prefabricated floor. You can browse to your working directory. I think I went too far. Here is my folder. As an analysis type today, it will be a heat flow analysis. So this choice is important because once you have made this choice on the analysis type, it will narrow down the options that are available in Diana. So for instance, by selecting heat flow, I won't be able to assign any structural element to my model. For the dimension, we are going to use 2D-dimensional. The model size, for the one who follows on a regular basis our e-learning session, you know that's something on which I insist. This is an important parameter because it will define the box or the outer dimension of the box in which your model should fit. So always make sure that it's big enough. So today I'm going to use 10 meter. For the measure type, I use hexaquad dominant and linear element. In terms of units, we are going to use millimeter, ton, Newton, second, Celsius and radian. So, as you could see from the slide depicting the cross-section of the model, we need basically to define 3 shapes for each layer, for the insulation, the concrete, and the top layer. And to do that, I'm going to use the Add Polygon Sheet option. And I will start with the insulation layer. For the method, I'm going to use coordinates, meaning that I have to input all the corner points. I have already prepared an Excel sheet with the coordinate of this point to save time. And then I copy them. And then I click Create. It will result in an insulation set under the shape. I can zoom in. We repeat the same operation for the concrete. I copy the point. Zoom out. So it's appearing blue because it's not yet created. So it's a kind of preview. And now I click on Create. And I see appearing under the shapes the concrete set. And finally, the last one, which is a screed. Copy. Zoom out. So you see the preview. And I create. So I have now my 3 sets. So for the insulation, the concrete, and the screed. What do we need to do next? We are going to do the property assignment. So for this model, it's heat flow, so we just need to assign heat flow property. So basically conductivity parameter for our analysis. So I go to the property assignment. I start with the insulation layer. I choose for 2D flow element, and I need to define the material that I'm going to call polystyrene. I choose for heat flow class and isotropic. And I'm going to specify a conductivity parameter, which in our case is 0.04. And I click on Create. I will repeat the same action now for the concrete floor. So I select the concrete, choose for 2D flow, and I define a set concrete. Also heat flow class isotropic, for which I define a conductivity of 2. And I click on Create. And then the last one, the screed, select it, choose for 2D flow, cement sand, okay, and here I input a conductivity of 1. And I create. So we have defined a condition, geometry. We have assigned property to the 3 layers. We are now going to move to the boundary condition, which is actually one of the key points of this example of today. And it will illustrate what I have been explaining about the boundary condition in my short presentation. So first I will start with basically the boundary condition at the bottom. So along this edge where we have a temperature of 10 degrees. So I'm going to define a thermal boundary condition. I call it external temperature bottom. It will be part of a set which is called external temperature. It will be applied to edge. I choose for external temperature, which will be 10 degrees. And here I need to define my boundary interface. So I'm going to call them boundary interface bottom. Type is boundary interface. It will be applied to edge. I select the 4 edges where I want to have this boundary condition. And then I define a material property. I call it heat transfer bottom. Heat flow, boundary elements. OK. And here I specify a heat transfer coefficient of 0.025. And for the discharge, I choose convection only. OK. I create this interface. And if I go back to my thermal boundary condition, you see now that my connection set on my interface are there. I can select them, and then I can click on create. And now if I go to connection under boundary interface, you can see my boundary interface at the bottom. And for the boundary condition, you can see the external temperature that I have defined. We are now going to repeat the same action, but for the top. So I define a second boundary condition, which I call external temperature top. So it's part of the set external temperature. It's applied to an edge. It's an external temperature, but this time it will be 20 degrees. And I'm going to define interface at the top. So I'm not going to select this one. I'm going to create a new one, which will be the boundary interface top. So the type is boundary interface. It's applied to edge. I select my edge. Yeah, here we go. So it's flow boundary, and I'm going to define a new material, which is heat transfer top. Okay. Here I'm going to specify the heat transfer coefficient of 0.0077, and again I choose for convection only. And I create this set. I get back to my boundary, and now you see that I have the 2 interface set, and I choose the top one, and I click on create. So now I can see that I have 2 boundary conditions, part of one set, the top and bottom one, and I have also 2 boundary interface. So our model is complete. For the boundary condition for the symmetry, I don't need to apply anything. So I can move to the mesh. And for that, we need to define some seedings. So I go for shape, and I'm going to use an element size of 20 millimeter. And for which, as we mentioned in the introduction, so I don't need to do it, I just do it for illustration. I go for the exact quad mesher type, and I select my 3 shapes, and I click preview, so I can see the number of division. So I go for 20 millimeter shape, element size, apply, and I mesh. So this is our mesh. So our model is ready. We are now going to move to the analysis setup, which will be relatively fast. So I go to analysis. I add a new analysis that I'm going to rename. So I call it heat analysis. And I'm going to add the steady state heat transfer. And that's it. I don't have to specify anything else. I mean, I'm just going to use the standard output of this analysis, that are the temperature and the flux, which is fine for this analysis. So now I just click and run. If we go to the message box, we see that the analysis has been performed. It goes pretty fast. It's not a big model. And we are going to look at our results, basically. So I go to the results environment, output. So for the nodal results, we have the temperature, and for the element result, we have the flux. So I present the contour of my analysis. I'm going to increase the number of layers. Contour plot. Going to increase that. I want to bring that to 20. So this is a distribution of our temperature. So you can see that you have a cold and a warm phase and a varying temperature inside. And if we look at the flux, present as a vector, and I'm going to increase the size of the arrows. You can see the direction of the flux in this model. So this model was performed with this insulation layer. It would be interesting to see what happens when you don't have this insulation layer. So I've already rerun an analysis without the insulation layer. So basically, from the model, you only keep the concrete and the screed. So if I go to the geometry, you see that we got rid of the insulation layer, meaning that your boundary condition on top is the same, but at the bottom, the interface is applied at the edge of the concrete, not to the insulation. So basically, when you perform the analysis and you look at the results, you end up with this variation of temperature. So you can see the impact of the isolation layer. You see that the temperature is lower here. And we can also present the flux. Why I cannot see them? Maybe I have to change. Here is a vector plot of the flux. So this is it for the live demo of today. So we have built a model, relatively simple 2D, on which we have assigned heat flow property by means of conductivity parameter. We have defined mixed boundary condition, so using flow boundary interface, and we have performed a steady state analysis. And we could see the temperature control plot and the fluxes resulting from this analysis. And we could also see what the impact of this insulation layer on this model. So this case studies, you can practice it at home. It's one of our tutorial, the heat flow of a prefabricated floor. So you can find it on our website. I would like to thank you one more time for attending this webinar, and I hope to see you next time. So have a good day and stay safe. Thank you. Bye.